Our brain is a perfect computer, and it needs only 20 watts to work. Today, nothing can compare with such efficiency. The strongest silicon-based computers need about 1 million times more power, and they are still unable to do all of the things our brain can handle. Do we want to switch our machines to organic chemistry and thus lower the energetic cost of computing and open the doors to numerous groundbreaking possibilities? Of course. There is, however, one problem. Unlike evolution, we don't have 1 billion years to accomplish that goal. That's why we need to work smart and with precision, and that means breaking through really small resolutions, lowering everything down to nanoscale. Let's think about the ultimate limit in this molecular approach to make new materials. The control of the shape and composition down to single atoms plays a crucial role in prototypical molecular circuitry. But are we able to see single molecules? Or even better, are we able to actually make them one after another?
In my laboratory at the Institute of Physics, we can not only see single molecules, like in the chemistry textbooks, but we can also synthesize them on demand on the surface. This approach provides molecules which are usually unattainable by classical chemical cooking. To avoid contamination and to drive the reactions into desired pathways, the experiments are performed in the ultra-high vacuum conditions, similar to those in the cosmic space.
We also provide them with a surface, a sort of two-dimensional world on which they can evolve. It's different from all of the realities provided by 3D nature world or solution chemistry.
The approach has proven to be extraordinarily successful in the generation of new molecular compounds with precisely defined topology and properties.
Of course, the synthesis of individual molecules on surface is still in its infancy. Obtaining a molecule that would have the required properties, and furthermore, not only one molecule but a whole bunch of them, is still severely limited. Therefore, for most applications, we need to combine classical chemical cooking and modern bottom-up design approach in order to successfully control and exploit the world of molecules.
We design molecules and molecular materials on demand by assembling organic and inorganic building blocks into larger coordination structures. What we are working on, we are trying to achieve multifunctionality. Specifically, we design luminescent materials that can transform ultraviolet light into other wavelengths and also can translate visible light photons into magnetization, and in this way we can make photomagnetic materials. The best part is that we can actually decide how all of this is happening by using knowledge from molecular chemistry, supramolecular chemistry and physical sciences. And that's pretty much it.
Well, pretty much, but not all. Our molecules have very specific and dedicated construction.
We design them by bridging various metal ions and cover them by additional organic components. This is the whole new way in molecules design. Thanks to our construction, luminescence and magnetic materials do not only emit light of desired wavelength, but can be also sensitive to magnetic or electric field, as well as other chemical or physical stimuli. Imagine a magnet that can shine or can be magnetized by light, inform us about temperature, and detect toxic gases. We are trying to open a new chapter in design of nanodevices based on molecules that can do many things at the same time.
Okay, now we have our molecules, so let's make something bigger out of them. A thin film. This is currently the starting point for making most nanodevices.
And of course the question is how we can make it. Fortunately, we can rely on nature. Such monomolecular films can be formed spontaneously on surface by self-organization process, the same wonderful process which is responsible for creation of these complex biological structures we are made of.
Such self-assembled monolayers, SAMs, can be formed on different materials by molecules which are chemically bonded to the substrate by one end, exposing the other end to the environment. These molecular nanostructures naturally create and control an interface between inorganic and organic world in most of organic electronic and biotechnological devices.
We are working on characterization of these cell monomers to understand their structure and properties. In last years, our research revealed kind of general mechanism which is affecting the stability of chemical bonds between the molecule and the substrate at the very interface. We think that that may help us to find a strategy to optimize chemical and thermal stability as well as a charge transfer through these cell monomers. If we succeed, I think we will really expand the applications of SAMs in the area of molecular electronics.
Of course, it is still impossible to create a brain, but we can do something else. We can build memory devices that can work in a way quite similar to a brain.
This is one of the most interesting directions in organic electronics. But there are others, like large area solar cells, field effect transistor, or light emitting diodes. Here in our lab, we can fabricate such device as a multi-layered structure made out of thin films of polymers. Large molecules purpose for such a goal. All of these organic electronic devices, in contrast to silicon electronics, are made by wet, it means solution-based method, also the one developed in our laboratory. The thickness of such a layer is a few dozen of nanometers, but their area is almost infinite. This is the key importance for chip fabrication. Also, we can mix several components in a solution, let them to self-assemble to form a device with spatially arranged regions, like a layer of semiconductor, a layer on insulator, in field effect transistor. In this way, we can simplify the production and reduce the fabrication cost.
The combination of polymers and the process of self-organization goes far beyond plain materials and can be exploited to form 3D objects, such as capsules. In our studies, we tried encapsulating poorly water-soluble drugs in water-dispersible polymer carriers and delivering them to the particular site of action in our body.
The carriers should be robust enough to survive the stomach juice and small enough to be efficiently transported by the bloodstream to certain cells, where they should release the cargo molecules, enabling their therapeutic action. We actually designed and fabricated such core shell nanocapsules in our lab. The capsules consist of natural oils such as olive oil and smartly modified polysaccharides, polysugars. Importantly, those capsules were found to be very stable in aqueous media. We stored them already for 2 years and can encapsulate variety of hydrophobic, active, valuable compounds. For example, together with our collaborators, we were able to show that efficient delivery of well-known common spice like curcumin encapsulated in our core shell systems can bring a tremendous therapeutic effect in curing hypertension. Very soon, I hope those novel carriers will appear on market filled with a number of valuable drugs, medicines, vitamins.
From a single molecule to complex organic electronic devices and nanomedicine, every path in our research guides us towards the future that needs less energy input, offers new therapies, and creates memory devices mimicking the work of the brain. As we continue to explore the possibilities given by the combination of organic materials and nanotechnology, we are paving the way for a more sustainable, innovative, and interconnected world.